Hello everyone, welcome to my channel. In today's video, we're going to do something a little bit different. We've never done this before in my channel, which is time series classification. I first knew about this type of task when I joined a Kaggle competition in April last year. So in this video, we're going to learn about time series classification, the definition of it, and then how to do it in general. And we will also learn about Rocket, one of the best algorithms out there to do time series classification. And lastly, I'm going to take you to revisit the competition and redo the competition using Rocket. Okay, let's study together. So time series classification is just like any other classification problems. The only difference is the input. In image classification, the input is image. So given an image, a classifier model needs to decide whether this image is an image of a dog or of a cat or of any other labels. And then this is an example of a text classification. So given a review, just a short passage, a classifier needs to decide whether this review has a positive sentiment or a negative sentiment. And with time series classification, the input is obviously the time series. Here we have two time series, the orange one and the blue one. The blue series belongs to the group state 0, while the orange series belongs to the other group, state 1. I made this plot using the dataset that we will see later. So yes, we are going to do binary classification. This type of task, the time series classification, is relatively less popular than other classification problems or forecasting, for example, but it's gaining more and more interest from many different fields. Like in business, the bank American Express has made some researches to find the model that could predict the probability that a credit card user go default, given the user's transaction history. The more common application of time series classification might be the human activity recognition. So this is used in many apps. You know that nowadays we have many apps to help us exercise, and these apps might use time series classification to detect whether we have done the exercise in the right way. To do all classification problems, no matter what the input is actually the same. We have only one principle, which is to make the problem look like a tabular data classification. One of the famous tabular data classification might be the Titanic problem. So I made an imitation of the Titanic tabular data. Each row represents the passenger, and each column represents the attributes that could explain the passengers. In a tabular data classification like this, the features are already given to us. But in image or text or audio or time series classification, we need to extract the features ourselves. And we're going to do that with Rocket. Actually, there are many types of algorithms out there to extract the features from a time series, but this is what we're going to discuss in this video. Okay, so kernel is our mean to extract the feature. Kernel is basically a filter. So we're using lots of filters actually, lots and lots of filters to extract the features out of a time series. Each filter will do a convolution process. So convolution is basically like a sliding dot product operation. I'll show you the example in a moment. And then a random. Why is it random? Because the kernels produced by Rocket algorithm are random. There are several hyperparameters that could be tuned in, but using Rocket, those hyperparameters would be generated randomly, so that the kernels that are generated are totally random. Okay, so I'm going to show you the example of a convolutional process. The first array here, like 7, 4, -1, and so on, is the time series. So let's say that we have a time series with length of 15. And then the orange array here is our kernel. Okay, so let's say that our kernel, our first kernel here, has the length of 7. All the weights are 0.1, and then the pi is 0. The dilation equals to 1, and no padding. Okay, when we have no padding, that means the first element of the kernel will meet the first element of the time series, and the last element of the kernel will meet the last element of the time series. If we have padding, if we set the kernel to have a padding, that means this one here. The center of the kernel will meet the first element of the series and the last element of the series. Okay, anyway, but we have no padding, so this is the right position of the convolution process. And this is the beginning. So in the beginning of the convolutional process, the kernel will meet a subseries, which is the first 7 values, and it will do a dot product operation. So 0.1 times 7, which is 0.7, and then plus 0.4 minus 0.1 minus 1 plus 1.4 plus 0.5 minus 0.7. Since we have set the bias to be 0, so we will add 0 here. Okay, the result of this addition will be stored in the first element of the resulting array. Okay, so I have done the calculation before, and it's 1.2. Okay, and then after calculating that, we slide the kernel by 1 to that point. Okay, so in deep learning, it's called the stride. The stride is 1. Okay, and then the kernel sees a new subseries. So now the subseries that it's looking at is starting from 4 and ends with -20. Okay, and then the dot product operation happens again. 0.4 plus minus 0.1 minus 1 and so on. Okay, and then the result of it will be stored here. And it will keep going like that. The process repeats by itself until the last element of the kernel meets the last element of the series. Okay, so I have done the process beforehand. You can check it if I make a mistake. And if I really make a mistake, I'm sorry, please leave the comment down. Okay, so now we have the resulting vector. The next step to do is to take the aggregate features. Okay, we will take 2 aggregate features. The first one is the maximum value. So it's like the global max pooling in deep learning. And then the second one is called the proportion of positive values. I set the index 1 here because we are taking the features out of the first kernel. Okay, so the maximum value of this vector is 5.2, so let's write that, 5.2. And then the proportion of positive values, it means that we have 9 elements in this array. So out of 9 values, how many values are positive? So we have 1, 2, 3, 4, 5, 6. So 2/3 of the array are positive. Okay, so for each kernel that is produced, we will have 2 features. In other words, if we have k kernels, we will have two k features in the transformed data. Okay, earlier I said that the dilation of this kernel is 1. So because of that, the elements of the kernel are placed next to each other. Okay, but what happens if the dilation is 2, for example? This is what will happen. Okay, so when the dilation is 2, the kernel will be spread out like that, so that each element of the kernel will meet every other element in the time series. And so when the kernel is first placed on the time series, it will look like this. So 7 will meet 0.1, and then -1 will meet the second element of the kernel, and then 14, and then -7, 8, 30, and 26. Okay, and the dot product is still the same. So 0.7 minus 0.1 plus 1.4 and so on. After the calculation is done, we store the results. We store the result here in the first element of the resulting vector, and then we strike by 1 point, so that 4 and then -10 and then 5, -20, and so on, that will meet the filter or the kernel. Okay, so I have done the process beforehand, and here's the resulting vector. The next step to do is to take out the features, the maximum value and the proportion of positive value. So the maximum value among these three elements is 7.7, and then the positive value, the proportion of positive values, is also 2/3. So in transforming the data set, the time series here, because we have two kernels, we will have 4 features. So like the first feature would be max1, and then the second feature is ppv1, and then the third feature is max2, and the fourth feature is ppv2. Okay, I said earlier that the kernels are randomly generated because we have so many hyperparameters to choose from. The first parameter is the length. The length is either 7, 9, or 11. Okay, so the length of the kernel is going to be one of these 3, and each value has the same probability. Okay, and then the weights. We saw earlier that the weights are all set to be 0.1. Actually, well, the weights are normally distributed with mean 0 and standard deviation of 1. Okay, and then the bias is uniformly distributed, starting from -1 ends with 1. And then the dilation here is on the exponential scale here. Look at x here. And x is uniformly distributed, starting from 0 to a, and a is defined to be this. So the dilation is set to be like this, so that when we lay out the kernel, the last element of the kernel would not exceed the series. Like the first time the kernel sees the time series, the last element of it won't exceed the series. And then with padding, well, you have only 2 options, with padding or without padding. Okay, and then the stride is always 1. So actually you have 5 hyperparameters here. You have 5 hyperparameters to tune in. And I said earlier that the rocket algorithm can produce lots and lots of kernels. I'm talking about thousands here. We will see later that in Python, the function of rocket can even generate up to 10,000 kernels. That's the default value. And even with 10,000 kernels being generated, the computation is still very fast. Okay, lastly, but definitely not the least, is the extension of Rocket for multivariate time series. So far we have only seen a univariate time series. You see, like, it's only one line, one array, like this. But the dataset that we will see later has 13 sensors, has 13 variables. So we definitely need to discuss how the Rocket algorithm goes when it's dealing with multivariate time series. It's a very little extension, actually. So let's say that the time series has 3 dimensions for now. And then let's say that the kernel is still 7. Okay. The kernel, I said earlier that the kernel has 5 hyperparameters. Now with multivariate time series, we have one more hyperparameters, which is the dimension. So perhaps the first kernel generated has 2 dimensions. Okay, so it's only, so this is the same kernel. The kernel is only 1, but it has 2 dimensions. And this kernel only doing the convolutional process with the first 2 dimensions. So let's say that the first kernel produced has 2 dimensions. It is one kernel, but it has 2 dimensions. And let's say that the kernel is doing the convolution with the first and the second dimension of the data. It will do the convolutional separately. So the first dimension of the layer with the first layer of the data, and the second layer of the kernel with the second layer of the time series data. With the first kernel earlier, the orange array, we have a resulting vector of 9 vectors, right? So 3, 4, 5, 6, 7, 8, 9. And now, since we have 2-dimensional kernel, that vector would be 2-dimensional as well. Okay, so since we did a convolution between 2 matrices, right? Because each, the kernel has 2 dimensions, and the time series, the sub-series, is in 2 dimensions as well. So we have a convolution of 2 matrices. So the result will be a matrix as well. Those vectors are supposed to be stacked on top of each other so that they make a matrix. The maximum value, like the first aggregate feature of that, would be the maximum value among all these 18 values. Okay, and the proportion of positive values would be the total positive values out of 18 values out there. Okay, so before we go to the application section, I want to show you the reference. You can try to read them to understand better. The first one is about the Rocket algorithm itself, and the second paper is, it's more like it's a bake-off. So it's a competition between algorithms. Okay, so here's the notebook. I already saved it beforehand. I ran it in Kaggle because, well, this is a Kaggle competition, and I guess it's the easiest for me if I do it in a Kaggle notebook. Okay, I'll show you first the competition that I was talking about. It's a tabular playground series. So actually the data set is kind of like a toy data. You see here, approachable data set. Okay, so it's a very clean data set, and then there's no imbalance between categories. Yeah. But the competition is real, and it happened not too long time ago. Anyway. So this competition is evaluated based on the area under the ROC curve, or AUC. When we make the model, we will use the metric AUC. And then we are given 4 files. So notice that the trained dataset and the labels are in 2 separated files. Here, in this competition, you'll classify, so we have a sequence of 60 seconds. So each person will be measured only for a minute. And so we have 60 data points. And then the labels, I actually showed you the labels earlier, and they represent 2 activity states. Okay, so perhaps the first group is walking or running, and the second group is doing another type of exercise. Task is test data set, and the sample submission is for submitting the prediction to the competition. Okay, so let's go to the code now. Firstly, we install the ASCII-time library because we're going to apply the rocket algorithm with ASCII-time library. I need to install in the Kaggle notebook because it's not pre-installed yet. Okay, after that, we import some libraries and list the input files of this notebook. And we can see that we have 4 files just in the description of the competition earlier. Okay, so first of all, notice that I wrote import TensorFlow here because I tried to use neural network models earlier, but I decided to leave it off and just use the Gradient Boosting Classifier, which is going to be applied using LightGPM library. I just want to focus on the rocket algorithm. And so, yeah, I try to make the model as simple as possible. Like, I just want to have 1 classifier instead of having 2 or more classifiers and doing ensembles of them, even though ensembling could guarantee a better AUC score. And then I also import the rocket class here. Okay, now let's load the data. I load the trained dataset as df, and then the test dataset as df test. Okay, every time I load my data, I get my total sequence and total subject, because each person might be measured more than once. So in the trained dataset, we have almost 26,000 sequences, but only 600 subjects. That means there must be many people who are measured more than once. So the subjects are coded like this, 47, maybe 40, and so on. And the sequence are ordered in this case, in this data set. So the sequence starts from 0 until 25967. This is, we're talking about the trained data set, by the way, okay? And notice that sequence and subject are both the index and the column names. Okay, we're going to remove these columns later. Okay, and by the way, I also have dropped the stop column. Stop is just an integer column starting from 1 until 60. So it's like the data point, data point. It's telling us, oh, this is the time point 1, time point 2, and so on until 60. So I can only imagine that each person has 13 sensors attached on his body, and the sensors are named like this: sensor 0, sensor 1, until sensor 12. And then this is the data set, the test data set. It's it has 12,000 sequences with 300 subjects. And notice that the sequence this is the head of the dataset, right? So the first sequence in the test dataset is 25968. And then it will keep increasing by one number by one. This will be important for converting the 3D. I'll explain that in a moment. Okay, so in the next cell, I just confirm that there's no missing values in those series. For example, like there's no technical error, so that the sensors went off for a bit, for a few seconds. All the sequence are complete. Like I said earlier, it's a very clean data set. And then I also load the label, the train labels data as df label. Okay, since it's a binary classification, it's either 0 or 1. State is the target variable. So we need to predict the probability that the state equals 1. Okay. After loading the data, I turned df and df test into a 3D matrix. Well, I told you earlier, right, that I joined this competition a year ago, like in April last year, and back then, ASCII-Time library didn't accept pandas data frame with only 2 dimensions. All inputs need to be 3D matrices. So yeah, that's why I had this code. But now ASCII-Time accepts 2D matrices, like pandas data frames with multi-index. But well, a part of it is because for my convenience, I want to keep my code here. And besides, I think 3D matrices are more intuitive to me. Okay, so ASCII-Time requires the 3D data to be like this. So the shape is the total sequence for the first dimension, and then the second dimension is the total variables. In this case, we have 13 of them. And then the last dimension is the total time points, which is 60 in this case. Okay, before converting the data frame into a 3D matrix, I drop the sequence and subject columns. Okay, and then this line here is to make sure that the total columns in both train and test dataset is the same. Okay, and then I make 2 slightly different functions to convert the to convert the datasets into a 3D matrix, because well, that has something to do with slicing in pandas. Actually, I could have typed iLoc integer location instead of just loc for location, because well, you know, in pandas, if you slice using the loc method, you need to give the index name. And I showed you that the test dataset, the first index of the test dataset is 25968 instead of 1, 2, 3, like that. So if I want to call the first sequence of the test dataset, I need to take that number, that big number. That's why I have to add the total sequence. Dot underscore sequence is the total sequence of the train dataset, by the way. Anyway, now the next cell is applying those functions, so converting my datasets into 3D matrices. And then after that, we can confirm that the df3d, which is the train 3D dataset, and the test 3D dataset are indeed in 3 dimensions. Okay, 13 represents the sensors, and 60 represents the time points, total time points. Okay, now let's do the visualization. So here's the code to do that. I randomly chose 15 time series from the state 0 group and 15 another different time series from the state 1 group. So here's the plot. So the left column belongs to the state 0 group. Okay, and we have 13 rows here because each row represents the sensors. Okay, we can see that sensor 3, actually sensor 2, sensor underscore 02, but it's the third sensor, has the most different plot than other sensors plot. Okay, and then in some sensors, like the second and the fourth sensor, we can see that the series from the right column have wider range than the ones from the left group or the state 0 group. And well, notice here we have the pink series, which has the biggest range, while in the fourth sensor we have the orange series. They represent different time series, okay? But in the first row here, maybe I should zoom in. Okay, so the pink series that is quite apparent in the first row, in the first sensor, and in the second sensor, they represent the same series. And then I feel in some sensors, like in the 9th and 11th sensor, the series from the state 0 group has clear cyclical pattern, while the series from the state 1 group don't have that. One more thing about this code is that I didn't set any seed to pick the series to be plotted. So when you run this code, you might get a very different looking plot. Okay, next we split the dataset into the train and valid. So we split the train dataset into train and valid. To do that, I set a seed. So when you run this code, you will get the exact same train and valid datasets. I firstly got the train ID and then the valid ID. And then this is just to make sure that we don't have any overlapping groups, that no series falls into two groups. And then in the cell, we slice the data frame 3D and the DF label so that we have the train and valid dataset. Okay, so to fit the rocket transformation, we train it with 20,000 instances or like sequences. Okay, now the interesting part is the rocket transformation. We first need to build the instance of the rocket, and I name it as trans because we want to transform with rocket, so trans. Okay, actually we have more parameters than this, but I set them with the default value. After building the instance, I fit the transformer to the training dataset and training label. And well, literally this happened in a blink of an eye. So immediately after I click the run button, I get this. It's really quick. I think they are very fast. This algorithm is very fast because they are just randomly generating kernels It's like they don't think about it, just randomly generate kernels. And then after getting those kernels, then we need to transform the datasets. So let me show you a little part of the real paper here. It's available for free anyway, so you can search for this paper. What it means by transforming is that you do the convolution operation and take the aggregate features, the maximum value and the proportion of the positive values. Okay, and like I said earlier, maybe I should show you the documentation as well. I told you that there are some parameters that I didn't set because I just set it to the default value, and one of them is in total kernels. And the total kernels is really 10,000 here. So the final dataset has 20,000 features. Okay, now let's go to the modeling part. After we have transformed the data, now we need to put the transformed data into a classifier. Now, if you read the paper, they will say that theoretically, the transformed data could be used with any classifier, even though they use the logistic regression and the logistic regression and the rich regression. And then in SK time, actually we have a function, a class of rocket classifier, which combines the rocket transformation and the rich regression. So yeah, I tried to do that. I tried to do rich regression, but the performance was quite bad. So that's why I didn't use that. I end up not using that. So what I used is the gradient boosting classifier. Okay, and to build the instance, I named it as LGPM mod. We use LGPM classifier to instantiate the class, and then I used 2,500 estimators. It's basically 2,500 trees. Okay, and then I set some parameters to avoid overfitting, including this. So call sample by tree means that every time the classifier builds a decision tree, it will only consider 90% of the total features. And I also set the seed so that when you run this, you will get the exact same model. After building the class, after building the model, we fit it. And the metric is AUC, because that's what the competition requires. Okay, I'm not going to show you the output, it's very long, but let me just show you the summary plot of the AUC. So this AUC score is for the valid dataset. Again, it looks really well. It improves really fast. So after around 100 estimators, the AUC is already 0.91. And then at the end of the fitting process, the AUC score is around 0.933. Okay, so now that we have the model, we can predict the model to the test data. I'm saving the prediction in the submission file. So I first load the submission file. So this is the state column again that we need to change or replace with our prediction. And then to predict the states, we use this predict probability. So it's not like a hard prediction like 0, 1, 0, 1, but it's more like the prediction of the sequence to be in the group state 1. Actually, predict proba method here will give us a matrix of two columns. The first column is the probability that the sequence is in state 0, or the first group, and because we want to take the probability that the sequence is in state 1, that's why we take the second column. And then lastly, I save the submission file to a CSV file. Okay, now let's see the output. So let's see the submission file. So my model, or our model, predicts the first sequence to be very likely in the group state 1. But the third sequence is very likely to be in the state 0, or in other words, very unlikely to be in the group of state 1. That's why the probability of being in state 1 is really close to 0. Okay, so this is the submission. And now I want to show you the result of this prediction, like the AUC score of this prediction in real time. So I'm going to click the submit button here. And then you can enter the description. And then just like that, you can click submit. Drum roll. Okay, so if you notice that this line, the top submission is being identical with the one below it, that's because this is a little bit of behind the scenes story. So when I tested my code a few days ago, I have tried submitting it. And so I know that this algorithm works really well. Now let me show you what I did a year ago. So like a year ago, I didn't use Rocket at all. I spent a lot of time learning Shapelet, another algorithm to extract the features out of a time series. So that's why I didn't get the time to learn and apply Rocket at all. And then the rest of the submissions used Shapelet as their feature extractor. And you can see that they are doing quite well. For the first year, for my first submission, I submitted the wrong column. So I submitted my first column of the prediction. That's why I got a very low score. Okay. And then starting from that, I keep improving it. And I guess the only difference between between this one and this one, version 8 here, is the number of estimators. So in version 8, I added more estimators in the GPM classifier, and I got the highest private score for the Shapelet algorithm. And then I could even get an even higher score using Rocket, even though it's just a small margin. Okay, so that's it for today's video. We learned about time series classification, and then we learned about Rocket, a very fast and a very good performing transformation for time series classification. These are the charming points of Rocket, I'd say. It is fast and it can get a very high accuracy. Okay, so thanks so much for watching. Don't forget to subscribe and like and share this video to your friends. And I'll see you next time. Bye-bye.